the title here, which is Sustainability and Information and Communication Technologies. Then, yeah, we are going to spend time what are really the different pathways to try to have more sustainable electronics today. But before starting really to dive in this topic, I would like to shortly introduce my research group, which is composed of approximately 30 researchers. One part of the group is really working on the use of MEMS, let's say fabrication techniques, to build up such kind of, let's say, lab on chip, where we can really test the mechanical or electromechanical properties of thin films to extract, for example, the fracture strain or the young modulus or the creep in different layers. And for example, one of our latest research was going to be published in Nature Communication is the extraction of the tenacity and the fracture strain of graphene. As part of the group, the other important part of the group is really working on what we call radio frequency SOI for silicon and insulator technology. And we have been working quite a lot on the development of new SOI substrate. We have developed, for example, the trap-rich SOI substrate, which is today used for any type of wireless devices based on SOI technology. We have been also working on different type of transistor architecture. We let's say, work on the modeling, on the characterization on wafer over wide frequency band of those new devices up to the design of front-end modules in this SOI technology. Okay, then I would like to share with you the different, what I think as the different factors that can explain the environmental impact of ICT. And we'll mention 4 of them here at least, because I have a limit of time to explain you that. And the first one that I'd like to mention is really the Moore's law. Yeah, the Moore's law that we all know working in microelectronics. We try to increase the number of transistors and to increase the chip density by a factor of 2 approximately every 18 months. And then we know that thanks to this, let's say, engineering work, we have the possibility today to have integrated circuits of a few centimeters square with more than 50 billion transistors for the microprocessors and 500 billion transistors for the memories. This is really fantastic. Of course, the main motivation here is to keep the production of those very complex integrated circuit at fixed low production cost. We have thousands of researchers and engineers working hard to keep track on this Moore's law, which is basically, at the end of the day, mostly an economic law. Really try to have more performance, higher density, and thanks to the fact that we have integrated circuit with a higher density, we can really keep the production cost at a low level. But what are the other costs that we have to pay to keep track on the Moore's law? And we have to mention here a few of them. One of them is when we move to miniaturization, we have, of course, very important pressure on the materials that you have to use to build up those integrated circuits. Here are represent the Mendeleev table, and I highlighted in light blue the different materials that we were using at the 80s for building an integrated circuits. Of course, you recognize here silicon. We use boron, phosphorus, or arsenic for doping. We have, of course, the oxygen to grow the gate oxide of the transistor and the aluminum layer here for the interconnections. In the 90s, due to already this downscaling of the transistor, we start to observe an increase of the access resistances, mostly the source, the drain, and the gate of the transistor. Then we proposed at the 90s, at that time I was in the engineering school, we proposed to use titanium or cobalt to have, let's say, a mix of silicon with those metal layers to have what we call silicidation process in order to reduce the resistivity of the source and drain and also gate contact. That was mandatory to keep, let's say, the performance of the transistor. But in 2000 has really a big shift, a big change in the microelectronics industry. You can see here highlighted in orange all of the materials that they are today used in microelectronics to keep track on the Moore's law. I don't have time, I don't have the expertise neither to explain all of these materials that they are introduced today, but you can recognize here germanium, which is mostly used for straining the channel and increase the carrier mobility. You can see here the hafnium oxide. It's now the most popular high-K dielectric used for the gate stack. And the main reason is we have to change the dielectric of the gate stack, because when we downscale the size of the transistor, it's not only the length of the transistor and the pitch between gate contact, but it's also the gate oxide thickness. And if it's too thin, you will have a very drastic increase of the tunneling current. And then to avoid that, we have to thicken the gate oxide, and to keep the same electrostatic control on the carriers in the channel, we have to move to high-K, high permittivity dielectric, and hafnium oxide is one of them. And then you have, of course, an explanation for the use of all of those materials in the processing of these, let's say, advanced CMOS technologies. And this high pressure on the materials, you can now, think about what would be the cost, what would be the impact. And I'd like to share with you here this graph, which represents the abundance in the earth crust of all of those different materials. And just be careful here, you can see that the Y scale, it's a log scale, then we have 10 orders of magnitude when we compare the most abundant materials and the more scarce material here at the bottom. Now, if you think about the extraction of those materials, for example, for iron, if you extract 1 ton of ore, you will have the average over the earth crust, approximately 330 kilograms of iron out of these 1 ton of ore. If you extract 1 ton of ore, but to basically get some platinum, you see here that in that case, we don't extract 330 kilograms, but just 3 grams of platinum. But for extracting those 3 grams of platinums, we have to consume the same energy for extracting basically this 1 ton of ore. Then if you look for the products and services of the 50s, this is really the material that they were used at that time. Today, we can really say that for all of the products and the services that we have out of the industry on the market, all of those materials are really used today. It means that we have always more extraction, always more energy, which is needed for the extraction of those materials, and more energy, as I explained here, because we need, let's say, much more energy for extracting the same quantity of material for those type of materials right here on the table. It means more energy for extracting those different materials, and this energy which is used, it's translate, of course, to more greenhouse gas emission. Another important factor is the increase of the process complexity. You can really see here on that graph, in the x-axis, you have the CMOS nodes from 90 nanometers, 2004, up to now, where we are approximately at 5 nanometers, or even smaller or shorter nodes today. And then you see the number of process steps is increasing drastically with the downscaling of the transistor. Today, we have more than 1,000 steps for building an integrated circuits. At the same time, what we observe is this very important increase of the sold chip. You can see here from the late 70s up to those years, we have an increase of approximately 9% of sold chips per year. That it's a very wealthy market in microelectronics. But if you add up those two let's say, function here, the complexity of the fabrication of those ICs, mostly due to the downscaling of the CMOS transistors and increase of the cell, you end up with these energy footprint and basically CO2 footprint of an increase of approximately 16% per year for the microelectronic industry, knowing that if we want to fulfill the Paris Agreement and the Treaty on Climate Change during the COP21 in 2015, they claimed that if we want to keep the temperature increase below 2 degrees C in 2050, we need to reduce all of the industries, all type of industry. They have to reduce by 5% each year the CO2 emission. We see here that microelectronics, unfortunately, is pretty far from that objective. The third important factor is new markets. You have heard, of course, about the Internet of Things and the artificial intelligence. Today, we can say that we are still in this big wave of mobile communication and the use of cloud services. But soon, we will see an increase, a drastic increase. This is at least the prediction from the market of the Internet of Things and the artificial intelligence. And of course, the production of those new objects will rely on the use of more ICs, means more, let's say, energy and CO2 emissions from this industry. And the fourth factor, you have certainly heard about the CHIPS Act. The CHIPS Act is not only in Europe, it's also in the US and also in Asia. And then, of course, one of the, let's say, consequences of this CHIPS Act is the increase of number of research product, but also industrial investment. It's really an economic war where we have, for example, here I just took the increased number of foundries. And you see we are going to increase by, let's say, from those years by nearly a factor of 2, the number of fabs in the next 3 or 4 years. This is really a major increase of the number of factories for microelectronics. And of course, related to this increase of production, we have an increase of the environmental impact of that industry. Of course, most of the people in the media, in the industry, but also in the scientific publications, they mostly focus on the CO2 emission. But of course, it's much more than climate change. You can find, of course, plenty of, let's say, scientific papers demonstrating the coupling between the way of living and the health of the planet. There are several planetary limits that have been already transgressed, and not only the climate change, which is represented here. You have the possibility today as a scientist to use different simulation tools to not only calculate the CO2 emission of any, let's say, products or processes or services in the field of science and technology, you have the possibility to really calculate, evaluate 16 impact factors, addressing air, water, soil emissions, the use of different types of resources and the impact on the ecosystem. And we have the possibility to not only calculate CO2, but also those 15 other impact indicators that I really encourage all of us to really, let's say, consider those, let's say, calculations, to at least have a compass, basically, to know what are really the hotspots and where we have really to concentrate our effort to reduce the footprint of that industry. And now I would like just to share with you the ongoing actions to really reduce the footprint of ICT at the industrial and also at the academic level. Just a few examples, of course. I don't have time to go to too many examples. One third thing that I would like to share with you is to say that methodologies are well established, which is called a life cycle assessment. There is even an ISO standard, which is the 14040, where you have this methodology that can be used basically to calculate the different types of environmental impact of any of your productions or services or process, considering really the full production chain starting from the raw material extraction, materials manufacture, the products manufactured, the use phase, and also the end of life. And we have, of course, a very important flux of resources and energy used, and of course, gas hot emission for all of those steps. Then you can really calculate different inputs of resources and calculate also the waste at each step. It's very important to make all of those evaluation if you really want to, of course, act on one of those stages. And then, of course, important also if you want to start, let's say, thinking about more circular economy or circular electronics in our case here. And what are really the, let's say, the ongoing projects today? There are a lot of different companies and research centers that they try to reduce the energy and water use during the processing in microelectronics. Of course, this is very good for the environment, but also good for the economic profit. And this is one of the main reasons that there's no really major questions there to really act, because it's also good for the economic profit. I can just mention here three examples, three different companies, UMC and TSMC in Taiwan, and ST Microelectronics mostly in France and also in Italy. And this is data coming from the CSR and the Corporate Social Responsibility report. You can see here the primary energy demand and also the water consumption of those three companies. And then what we can observe here, it's the, let's say, a reduction, even if it's a low reduction of the primary energy demand for ST Microelectronics and UMC. The same story for the water consumption for those two companies. This is good during this period of time, even if we see that the reduction is not really drastic. But we can observe that for TSMC, it's very hard, even if they try to reduce the power consumption and the water consumption, we observe that unfortunately we have this very important increase during that period of time, and it's still increasing today. And this is mainly due to the fact that this is one of the companies that they will try to still keep track on the Moore's law and really work on the ultimate scaling of the CMOS integrated circuits. But what we have to keep in mind when you read those kind of reports, you can see here that the units that they are used for the energy consumed and or for the water consumption, this is megajoule per centimeter square of wafer, and the same thing here, and it's per unit area. But knowing that during the same period of time, we have an increase by 70% of the salt integrated circuits, unfortunately, even if they make a lot of efforts to reduce the resources used in the processing of those ICs, because the salt of ICs has been increasing drastically during the same period of time, we have an absolute increase of electricity and water consumption. And keep that in mind, the absolute impact, and not just stick with relative effort made by those companies. Second effort is try to recover and recycle materials during the processing. This is good again for environment, but it's also good for the economic profit. And this is the reason that is still in place in many of those foundries, because you have to know that when you deposit thin films, for example, evaporation or by sputtering, most of the metal is deposited over the chamber walls, depending on the process method, that could be over 80% of the metal is really covering the walls and not really the substrate, the wafer, the target, basically. And this is really important part of the material that can be really recovered if they use the correct technique to recover the material. And of course, they will have to undergo to a certain purification before reusing that material in the process flow. But there are several projects ongoing in the industry to realistically recycle the metal inside the company itself. Now, there are also projects really working on new chemistry, but it's mostly at the research and development level. And then in that case, the main motivation is to fulfill the upcoming legislation in Europe. We can find several European projects that they really work trying to replace, to substitute some of the chemicals for stripping, for wet etching, cleaning, and decontamination. We can mention here, for example, also the evaluation of biosource water-soluble resist for avoiding solvent and alkali-based developers. And for example, at CLIT, in collaboration with ST Microelectronics, they try to introduce chitosan biosource resist for the back end of line, and they start to have some successful research for that. Now you can use, of course, LCA, life cycle assessment, to think about really the use of the starting materials of your process. It means the substrate. And there are a lot of different works working on substrate engineering to use the correct substrate for the correct application. And for example, here we have made a study in my group studying different types of substrate for high frequency and high power applications. And then be careful here, the scale you see for those two indicators, which is the global warming potential, basically is the CO2 equivalent emission, and the biotic depletion potential. And we see that for the same, of course, performance, it's very important try to move to silicon-based substrate, even if you can use on top of those silicon substrate 3-5 materials to, of course, take advantage of those wide band gap semiconductors or high mobility semiconductors. Another, let's say, study that we made in my group is for the spiking neurons or neuromorphic systems. You might know that most of those sparking neurons, they use metallic contact, and the metal that they use, it's gold for any publications. This is really the metal that they use. Then we made the LCA of the full process, and then what we observed that the gold evaporation for two indicators that are represented here, which is the primary energy used per wafer, and here the CO2 emission per wafer. They are really the most contribution, the most important contribution to those two indicators. And if we replace the gold by aluminum, we can really reduce by 25% the electricity use, and also the global warming potential by 43%. Sorry. Of course, what we have to do is be sure about the performance and the reliability of this kind of spiking neurons. And this is what we have tested, and we have demonstrated that we can really obtain the same performance, the same reliability, changing the contact from gold to aluminum for this kind of device. Then substitution is, of course, a pathway to reduce the impact of the microelectronics industry. Now, I'd like just to mention a very important European project that's going to start very soon, grouping 60 partners from 12 different countries. This is Genesis. Genesis is really trying to, let's say, have pretty ambitious targets, try to reduce by 50% the hazardous materials used in the processing, reduce by 30% the emissions and waste, and try to improve the recycling of rare materials during the processing. Now I would like to finish up my presentation by insisting on one of the, let's say, stage of electronics, which is not really well studied or nearly no study in the literature, which is the end of life of electronics. You know that if if we just see numbers, most of the electronics, unfortunately, go to landfill, approximately 70%. Only 10 to 15% are recycled. And when we say recycled, it's try to retrieve some of the materials out of these electronics. And of course, the best would be try to repair, try to reuse those electronic devices. And there is an increase of the market of the, let's say, repair and reuse of, for example, a smartphone here. But still, keep in mind that unfortunately, there is no real solid solution for the end of life electronics. The best, it's recycling today. And when we say recycling, as I said, we try to recover some of the material out of these scratch electronics. And it's really one of the major company in the field in Europe is Umicore in Belgium. And this is public information. They can really technically extract approximately 17 out of the 60 or 70 elements that you can find in a smartphone or any electronic devices. But actually, they just extract, they try just to recover 4 to 5 materials, but because they are those only 4 or 5 materials that they are profitable and just at the academic, let's say, level. And then those materials are gold, silver, platinum, palladium, and copper. And then the reason that all of the other materials are, still too cheap, let's say, to extract from most of the countries, the southern countries. And this is really the main situation. And instead of thinking about really the recycling, I think that it's very important to think about more circularity, try to use those shorter loops and try really to better reuse, repair, and why not also repurpose those electronic devices and components at the end of their first life. And this is basically what we try also to propose in our research group, and starting, let's say, 1 year ago, to think about dismounting different, let's say, complex devices, electronic devices. I take here the case of the smartphone. This is a smartphone from Fairphone. That is the Dutch company, that they would think about the different ways of assembling a smartphone to ease the repair. And in our case here, what we try to do after a first life of the smartphone, when it's not really, let's say, possible to refurbish that smartphone as a new smartphone, we can really try to reuse some of those components to build up a new, let's say, electronic device. And this is what we have demonstrated with this researcher, Nicolas Bruce-Mans, has presented that the possibility would be to reuse those integrated circuits or modules to build up new electronic systems. Okay, we don't have time to go to details, but this is really a project that I believe that really can really, let's say, help us to have a more circular electronics. Now it's time already to wrap up my presentation. I would like to really insist on the fact that today we have the methodology, we have the life cycle assessment method to really reveal trends at the early stage of development of any type of technology. Then we have to use those methods to basically measure and quantify the hotspot of any production. Of course, this is not easy. This is pretty complex, not to use the methodology, but to access to data, because there are some might be some IP issues. And this is something, a topic on which we have to work with the industry to see how we can have an efficient data collection. LCA is not at the end of the day. This is not sufficient. We have to study really the rebound effect and really to learn about the consumer behavior. To do so, we need to have really transversal collaborations to adopt a holistic approach. And for that, this is really a collective work We have to work together between industry, academy, regulations, citizens, social sciences. And in my group, we are, launching different types of research projects where we have all of those stakeholders ready to come up with some new ideas, new way of defining electronic products. Yeah, there's no doubt that our techno-liberal societies encourage us, as researchers and engineers to develop creative distraction, how it's called by philosophers. And it's really time, to my point of view, to really think about appropriate and appropriable technologies. And I'd like to finish up with this last slide. We have been driven those last 50 years in microelectronics by performance, technical performance, and economic profit. And then it translates to those four different figure of merit, so KPI, power, performance, cost, and area. Now, if we, start thinking a little bit differently, I'm not saying that we have to avoid those indicators. We have to, let's say, force us to think about even more indicators, think about the social impact and environmental impact of what we developed. And in that case, we have to really imagine what would be the electronics tomorrow, and not only focus on the artificial intelligence, but there are other electronics that we can really produce that they are going to take care at the early stage of development, more factors than just the performance and the economic profit. Yeah, like just to finish up my presentation by acknowledging a few people, the chair of excellence at CLT, many researchers, of course, of my group, and those, let's say, scientists that we have directly participated to let's say, the slides that I have presented today. Thank you. Thank you very much for your attention.